Hello, I'm Mike McCulloch. Today I'm going to answer a question that I've been asked quite a lot, and that's a very important one. So, as you know, galaxies rotate far too rapidly at their outer edges for visible matter to hold them in. So, of course, the usual answer was to add dark matter, but to increase the gravitational pull inwards. But dark matter hasn't been seen, and it's an extremely unscientific hypothesis. So I've suggested quantized inertia, which has a mechanism within it that reduces inertial mass for extremely low accelerations, such as found at the edge of galaxies, such as found there. But the very interesting question is that, okay, quantized inertia reduces the inertial mass for stars at the edge of galaxies, so reduces the centrifugal force outwards and stops the galaxies flying apart, even so you don't need dark matter anymore. But the trouble is that although the average acceleration of the stars is extremely low there, the acceleration of the stuff within the stars, the atoms, hydrogen and helium, is extremely high. So how can these two things be reconciled inside quantized inertia? So the answer is, and I've tried to show this answer using this diagram here. So this shows the yellow circle shows a star, which is going around in its orbit of the galaxy, so it's moving upwards. You can see the orbital speed is the arrow pointing upwards, and its acceleration towards the center of the galaxy is shown by the arrow pointing left. So the star is being accelerated toward the galactic center. And you can see the star itself is yellow, and I've shown the atoms within it in schematic form using the red dots shown here. And I've shown their small, the extremely large accelerations with the arrows. So the accelerations associated with the atoms have associated with them Rindler horizons. So each atom has a Rindler horizon, which I've tried to show with these sort of boomerang shapes. That's supposed to represent the Rindler horizon. So each atom has a Rindler horizon, which is fairly close to it because the acceleration of the atom is large. The star is extremely hot, so the atoms are accelerating, moving around very fast. So you can see these boomerang shapes around the star associated with all the different atoms. And I've shown 5 atoms, but there are actually, of course, billions of them. So these Rindle horizons are roughly equally distributed around the star. You can probably see that. Although I've only shown 5 atoms here, they're already quite uniformly distributed. And with billions of atoms, they'll be very uniformly distributed. So the Rindler horizons will pull on the atoms, pull them back against the acceleration. These are relativistic horizons caused by the acceleration and in the opposite direction to the acceleration in each case. But you can see that they're symmetrical around the star. So they won't pull on the star itself. These Rindler horizons will not overall produce a pull on the star. They'll all cancel out. Okay, so that's the individual accelerations of the atoms, but now we have to consider the motion of each of the atoms as they orbit around the galaxy within the star. So I've shown the Rindler horizons for that acceleration on the right-hand side within the kind of circle there. And the acceleration of the star around the galaxy is extremely small, so these Rindler horizons will be very far away. But I can't represent that in a diagram, so I've shown them next to the star. But you can see they're quite far away. And they're all within this circle, and they're all pointing in the same direction. And what these Rindle horizons will do is they will pull the star to the right, towards themselves. So these Rindle horizons will produce an overall effect on the star. They will pull it to the right. And these Rindle horizons represent the inertial mass of the star itself as an overall entity, if you like. Whereas the other Rindler horizons I was talking about before, that are symmetrically distributed around the star, they represent the inertial masses of all the individual atoms. And so this shows that this answers the question, that the accelerations of the individual atoms within the star cause the Rindler horizons that are uniformly spaced, because it's kind of random, and they don't affect the star overall. But the acceleration caused by the acceleration of the star and the galaxy does have an effect, because the Rindler horizons are all on one side of the star, so they pull on it. And of course, when the accelerations are very small indeed, these Rindler horizons move back so far that they're just about where the cosmic horizon is anyway, so they don't make a difference. And so for very low accelerations, the inertial mass disappears. The overall star-based inertial mass disappears. And so you get, so quantized inertia predicts galaxy rotation without the need for dark matter. But the other thing that this means is that there isn't one inertial mass. There's a separate inertial mass for every interaction you have, which is quite a change to physics. We think of a body as having an inertial mass, which is almost like a label which is attached to the body, and it's inherent in that body. But quantized inertia is different. In quantized inertia, the inertial mass is not does not have one single value. It has a different value for each interaction, depending on what the size of the mutual acceleration is. And this makes it far more complex in a way. And this is yet to be modeled accurately, but it can be, as shown here, it can be different on the microscale and the macroscale. Okay, so I hope this has answered the question, and I look forward to making another one of these tomorrow. Goodbye.